Let's look at converting between polar and rectangular coordinates, shall we? Okay, so rectangular coordinates is more common. So if you have a point, say 4, 2, what that means is you go over 4, you go up 2, that's the point 4, 2. But there's just as good an argument for saying, hey, I want to get to a point. Why don't I say rotate 60 degrees and go a distance of 3? In fact, if you're traveling, it's probably faster to turn to the point and go directly than go this direction. So this is more common, but there might be uses where this would be more efficient. The question is, how do we convert between the two? So let's set up our equations to start with. If you had theta and you had r, this is a right triangle, how would you get x and y? Well, how are x and y related to theta? Well, you remember that cosine of theta is equal to adjacent over hypotenuse, so it's equal to x over r. So what's x equal to? X is equal to r cosine theta. That's going to be one of your key equations. How's y related to r and theta? R and theta, let's see, opposite over hypotenuse is, of course, sine theta. So y equals r sine theta. Okay. Well, let's say you're going the other direction. You have x and y, and you're trying to get r. Well, I happen to know that r squared equals, I'll just write it over here, r squared equals x squared plus y squared. That's all good. Okay. And then how would you relate theta to x and y? Well, this is the opposite and the adjacent side, so tangent of theta always equals y over x. Now I'm going to put a little asterisk here. Those are my 4 key equations. I put the asterisk there because when you're trying to get from y over x to theta, you're going to be tempted to use tan inverse. That's just fine, but remember the range of tan inverse doesn't let you get everywhere. So you have to use common sense about what quadrant this rectangular coordinate system gets you to before you use tan inverse. Okay, so let's do a couple of examples. Let's convert 2 120 to rectangular coordinates. Okay, so I'm looking for something that's an x-coordinate, a y-coordinate. I have theta and r. If you think about this, I'm sort of in the second quadrant, and because that's 120, this distance is 2, and I'm looking for x and y. So essentially what I have is I have x and y, using those top 2 equations, is 2 cosine 120 to sine 120, and these are reference angles, so you remember that at 120 cosine is -1/2, so 2 times -1/2. Sine is √3 over 2, so this equals -1, √3. That's the rectangular coordinate description of this point in polar coordinates. They'll both get you to the same place. Okay, now let's work our way back. Let's convert let's say -4, 3. Nah. Let's do -3, 4 to polar coordinates. Okay, so I know how to get here in rectangular coordinates. 1, 2, 3, 1, 2, 3, 4. Okay, how do I get, that goes to the origin. How do I get that angle? How do I get that radius? Well, certainly if I knew this length and I knew that length, I could get the radius by adding the squares of those two. So -3 squared plus 4 squared equals 9 plus 16, which is 25. If that's r squared, then of course I've given myself a pretty easy problem. R is 5. that's the distance. How do I get theta, though? Well, I know, of course, that tan theta equals 4 over negative 3, and I can plug that in to a calculator. I'm just going to get an estimate. If I plug in, say, theta equals tan inverse of 4 over negative 3, you're going to get something that's approximately, say, negative 53.13 degrees, if you're in degrees. Now, you can see that tan inverse only outputs things in this quadrant. This is the angle that'll get you this slope, but I want to be over here. So what do I do to get to the one I want? Well, to go from here to the other side, I have to add 180 to this. So, adding 180, let's see, that's 126.87, and so you're going to put this in polar coordinates by 5, comma, 126.87 degrees. There you have it. That's the polar description of this point.